Welcome again to the class. Last time we have been discussing about the velocity and acceleration relations for a rigid body when viewed from two different frames of reference. One frame of reference is a ground frame of reference, and another frame of reference was a moving frame of reference with respect to the ground. So as far as the formulas we had and what we had discussed yesterday, the question was like we had, let me share the screen with you. As far as the formulas we had discussed yesterday were concerned, we had a formula. We have two frames of reference. One frame of reference was a ground frame of reference, and this is the origin of the ground frame of reference, which we called as O. And we had another frame of reference, which we call as beta, and this is the origin of that ground beta frame of reference, O prime. And this was a rigid body at P, which was under investigation, whose motion was observed by an observer in ground frame of reference and by an observer in moving frame of reference. And the expressions that we obtained yesterday were by drawing the vectors from O dash, O to O dash, and from O dash to P, also drawing the vector from O to P. The expressions that we wrote yesterday were, we had velocity of P with respect to ground frame of reference, that's velocity of P with respect to ground, with respect to a frame of reference which is not moving, is equal to velocity of P with respect to a moving frame of reference, that is velocity of P with respect to beta, plus velocity of beta with respect to ground frame of reference, that is velocity of O dash with respect to O. This is also velocity of beta with respect to ground, okay, because O dash belongs to beta and O belongs to J. So velocity of O dash with respect to J is as same as the velocity of beta with respect to ground frame of reference. Plus the expression we had, the last one, that is angular velocity omega, angular velocity of beta, okay, angular velocity of beta with respect to J, ground frame of reference. So we can also write this as omega beta or omega beta with respect to J to make it more precise. Cross product with the radius vector drawn from O dash to P. So we had our O dash P. This was the expression for velocity that we had written yesterday. And in the same way, we had the expression for acceleration as well. Okay, now let's try to use the expressions for the velocity and acceleration in solving the problems. Let's use these expressions in solving the problems we have in hand today. So as far as the problems are concerned that we have in hand today, we have a problem 16.18. As far as the problem is concerned, it says at the instant shown, at the instant theta is equal to 60 degree, we have a rod, okay, there's a rod, this is a rod, and attached with this rod is a collar. Attached with this rod is a collar, okay, so this is a collar. As far as the collar is concerned, the collar slides on the rod, okay, so this collar slides on the rod, okay, it starts its motion from here, goes downwards. This is the motion of the collar. As far as the motion of the rod is concerned, the rod swings, okay, it rotates about an axis passing through point O. So we can say that rod is having oscillating or rotatory motion. The motion of the rod is a rotatory motion. As far as the motion of collar C is concerned, the motion of collar C is translatory motion. It translates. Now the question says, at the instant shown, theta is equal to 60 degree. We have an instant where the angle subtended by this rod with the x-axis, the x's are given to us, is 60 degree and has an angular velocity of 3 radian per second. And this rod is having an angular velocity of 3 radian per second. Angular velocity it must be having because it's undergoing rotational motion, and a body in rotational motion does have angular velocity as well as the angular acceleration, and its angular velocity is 3 radian per second. And it has an angular acceleration of 2 radian per second. We are also given that its angular acceleration is 2 radian per second square, okay. Now what will be the direction of the angular velocity and angular acceleration? The direction will be obtained. These are just the magnitudes. 3 radian per second and 2 radian per second square are the magnitudes of angular velocity and angular acceleration respectively. What will be the direction of angular velocity and angular acceleration? That we will be obtaining with the help of the right hand screw rule, okay. Curl your fingers in the direction of the given angular velocity, the direction of the thumb will give us the direction of the angular velocity as well as the angular acceleration. So if you look, if you curl your fingers in the direction of these arrows, the thumb will be in this direction. That is essentially the negative z direction. Okay, so angular velocity and angular acceleration is along the negative z direction. Now again it says, at this instant, the collar C travels outward along the rod when x is equal to 0.2 meter. So when the distance between the point O and the collar is 0.2 meter, okay, when the distance between point O and the collar is 0.2 meter, the collar is moving outwards, okay, the collar is translating on the rod with a velocity of 2 meter per second. Its velocity of the collar is 2 meter per second, and an acceleration is 3 meter per second square, and its acceleration is 3 meter per second square, both measured relative to the rod. Now this is important, that the collar velocity and collar acceleration is 2 meter per second square and 2 meter per second and 3 meter per second square. Okay, so velocity and acceleration of the collar is measured with respect to the rod. So this is the velocity of the collar with respect to the rod and acceleration of the collar with respect to the rod. Okay, now determine the Coriolis acceleration. We have to find the Coriolis acceleration and velocity and acceleration of the collar at this instant. The question says, find the find the velocity of the collar at this instant, find the acceleration of the collar at this instant, and find the Coriolis acceleration of the collar. So we have to find three things of the collar. We have to find the velocity of the collar, we have to find the acceleration of the collar, we have to find the Coriolis acceleration of the collar. What is very important to us is we have to find, the question says determine the velocity, acceleration and Coriolis acceleration of the collar, and the question is silent. The question does not tell us with respect to which we have to find the velocity and the acceleration. Do we have to find the velocity and acceleration with respect to the rod or with respect to the ground? I have been saying since yesterday, since the previous class, that when the question is silent about the frame of reference, it is quite indicative that he's talking about the ground frame of reference. That is, we have to find the velocity of the collar with respect to the ground, acceleration of the collar with respect to the ground. This is what we have to find out. Let's first of all write down what things we have been provided. First of all, before you go ahead, denote your frames of reference. Okay, so see, as far as the rod is concerned, the rod is rotating. It says the rod, angular velocity of the rod is 3 radian per second, and angular acceleration of the rod is 2 radian per second square. And the question and the author is silent about with respect to which. So it simply means that it is with respect to the ground. So we are given velocity of the rod with respect to the ground, angular acceleration of the rod with respect to the ground. And since he is talking here that we are given the velocity of the collar with respect to the rod, acceleration of the collar with respect to the rod, we have to find the velocity of the collar with respect to ground and acceleration of the collar with respect to the ground. Okay, so we have two frames of reference. We have the ground frame of reference, so we choose this to be our ground frame of reference, O, and we choose rod to be our second frame of reference. We choose rod since the rod is moving and we are given one velocity and acceleration with respect to rod becomes one more frame of reference. So as far as rod frame of reference is like your beta frame of reference. It is beta rod because rod is rotating, rod is moving, velocity and acceleration are given with respect to the rod. So rod becomes beta frame of reference. And as far as the ground is concerned, the ground frame of reference becomes your J frame of reference. Okay. Now see here, when we were deriving the formula, we had, this was the O prime was the center of the beta frame of reference and O was the center of the ground frame of reference. Now here what is happening, this question is a bit easier in the sense that both the frames of reference is having the same origin. Okay, we are having O dash and O are at the same point. The ground frame of reference and the rod frame of reference or the beta frame of reference are having the same origin. So what we have to do now, this is quite easy problem for us. So first and foremost is, first of all, define your ground frame of reference. Okay, so while we define our ground frame of reference, we have to take three axes, which we say X, Y, and Z, and put them at an origin, call that as a ground. Since if you look at this hinge, okay, this hinge out here, this hinge is fixed, so we will treat this hinge as our ground frame of reference. Okay, so as we are treating our hinge to be the ground frame of reference, so what is happening, as we are treating this hinge to be our ground frame of reference, so let's suppose this point O is the origin of our ground frame of reference, and we take an axis in this direction, write it with capital X. This is the x-axis of our ground frame of reference, and this is the y-axis. This is the y-axis of our ground frame of reference. So this defines our ground frame of reference. This is our ground frame of reference. So let me highlight it a bit. So this is our ground frame of reference. Our ground frame of reference, sorry, our ground frame of reference is over here. This is our ground frame of reference. Okay, this is the origin of the ground frame of reference. This is x-axis of the ground. This is y-axis of the ground. Now, after defining it, what we have to do, we have to define the x and y-axis of our rotating beta frame of reference. If you look now, where will we select the beta? This rod is our beta frame of reference. Okay, the rod is our beta frame of reference. So we take an axis along the axis of the rod and treat that as x-axis of our beta. Okay, this is the x-axis of our beta frame of reference, and take an axis perpendicular to x-axis, write it with small y. This is the y-axis of our beta frame of reference. This is the y-axis of our beta frame of reference. So what is being denoted by red? What is being denoted by red is our ground frame of reference, and what is being denoted by this blue lines, that is our beta frame of reference. Okay, while you solve these questions, you need not to draw them as I have drawn, but you can have a picture in your mind what is the ground frame of reference and what is the beta frame of reference. Okay, now the question is, look here, the origin is common. The ground frame of reference and the beta frame of reference is having the same origin, that is point O. After writing these, after drawing the frames of reference, now what we have to do, write down the velocity equation first. So we will write velocity of, so as far as, in order to help students, make it easy for them, so what I am writing, I will, since what is the object for us? We have a ground frame of reference, we have a beta frame of reference, and we are observing the motion of the collar. Okay, so we are observing the motion of the collar. Okay, so motion of the collar is being observed with respect to beta frame of reference as well as with respect to the ground frame of reference. So we have to write the velocity and acceleration equation. We have to write the velocity of and acceleration equation for what? We will be writing velocity and acceleration equation for the collar with respect to the rod frame of reference and with respect to the ground frame of reference. So we will write, we have velocity of, from the previous equation, we will write velocity of collar C with respect to ground becomes equal to, okay, or I will first write the standard equation with which I will compare it then. The equation we have derived is velocity of P with respect to ground is equal to velocity of P with respect to beta, with respect to moving frame of reference, plus velocity of beta or velocity of O dash with respect to O, B dash with respect to ground, plus angular velocity of our beta with respect to ground, cross product with radius vector drawn from O dash to point P. Okay, as far as our O and O dash are concerned, our O and O dash here is at the same point. Okay, so P is the point which was under observation, so we have collar under observation. We'll write velocity of collar with respect to ground is equal to velocity of P with respect to beta. That is, velocity of P is our collar, velocity of collar, and beta is our rod, velocity of collar with respect to rod. Okay, plus velocity of O dash with respect to O. Okay, so we have velocity of O dash. O dash is the origin of our beta frame of reference, and O is the origin of our ground frame of reference. And you see that both the 2 points are at the same position for all. They always remain. O and O dash is always fixed here. So velocity of O dash with respect to O will be 0 because the origins are not moving with respect to each other. So you can directly write at, for our case, this is 0 because they are coincident 2 points. They are not moving with respect to each other. So this velocity term will be 0. So we have angular velocity of beta. We have omega beta, angular velocity of beta. Our beta is rod. So angular velocity of the rod with respect to the ground frame of reference and its cross product with R O dash P. O dash P is the the vector drawn from our beta frame of reference to point P. That is, our point P is our collar. That is, if we draw the vector from O dash to collar, it will be along x-axis. Okay, it will be along x-axis, and its magnitude will be how much? Its magnitude will be 0.2. So we'll write this as, or I will write here, this is the vector drawn from O dash, our point P is our collar, that is C. So we will write this velocity of collar with respect to ground. We don't know. We have to find the velocity of the collar with respect to ground. This is not given to us. We have velocity of collar with respect to rod. How much is the velocity of the collar with respect to rod? This is given to us. The velocity of the collar with respect to rod is 2 meters per second. So I will write this as, this is 2 meters per second, and it's along x-axis. So it is I cap. Since we are measuring it with respect to the rod, so we have to take the rod coordinate system. Our rod coordinate system is 2 meters per second, and with respect to rod, it's along x-axis. So this is 2r plus. Then we have omega r with angular velocity of the rod with respect to the ground. That is given to us. Angular velocity of the rod with respect to ground is given as 3 radian per second, and it's along negative. If you curl your fingers, it will be along negative z direction. So it will be minus 3k cap. This is minus 3k cap. This is given to us. And we have to take its cross product with, we have to cross it with r radius vector drawn from O dash to C. As we draw the radius vector from O dash to C, its magnitude will be 0.2 meter, and it will be along x-axis. So it will be 0.2 I cap. So that becomes equal to, that's equal to 2I. Okay, this is 2R. That is K cross I. How much is K cross I? We know this is our I cap, this is J cap, and this is our K cap. Now we have K cross I. As far as K cross I is concerned, we are going in the cyclic order. K cross I is equal to J, and it's plus J. So it is 3 into 0.2 is plus minus minus. It is minus 0.6, and K cross I is equal to J cap. Okay, so this becomes our velocity of the collar with respect to ground. So if we are questioned, what is the velocity of the collar with respect to the ground? We will say the velocity of the collar as observed by the observer on the ground. The velocity of the collar as observed by the observer on the ground is equal to how much? It's equal to 2I minus 0.6 g. This is the velocity of the collar with respect to ground. Okay, let's check it, what the author has given us. As far as the velocity of the collar with respect to ground is, see here, it is, sorry, if you look here, the answer, what the book has saying, the answer that we have obtained is velocity of the collar with respect to ground frame of reference is equal to 2I minus 0.6 J. Okay, let's see what the book is giving answer. Oh, sorry. So as far as the answer from the book is concerned, the answer from the book is same. We have the answer from the book as the velocity of the collar is here, 2I minus 0.6 J. That is 2I minus 0.6 J. And the unit of velocity we know is meter per second. So we have solved the first portion of this question. So as far as the first portion of the question was concerned, the first portion of the question was talking about the velocity of the collar with respect to the ground. Now we have to find the acceleration of the collar with respect to the ground. Now let's write the expression for the acceleration in the same way. So we'll write, as far as the expression for the acceleration is concerned, we know acceleration of the collar with respect to ground is equal to acceleration of collar, or I will write acceleration of the expression that we have in hand, acceleration of P that we have derived yesterday with respect to ground, acceleration of point P with respect to ground is equal to acceleration of P with respect to beta plus acceleration of O dash with respect to ground, acceleration of our beta with respect to ground, plus angular acceleration of beta, with respect to angular acceleration of beta with respect to ground. This is what we have written yesterday with respect to ground, cross product with the radius vector drawn from O dash to P, RO dash P, RO dash P, minus angular velocity of beta with respect to ground square, sorry, this is not in vector form, square RO dash P vector, RO dash P vector, bracket close, plus twice angular velocity of beta with respect to ground cross product with RO dash P. Okay, this is the expression for acceleration. Okay, if you look at the number of terms, we have one term, two terms, three terms. Okay, this is fourth term and this is the fifth term. We have five terms of acceleration in this. Okay, we'll be explaining in three-dimensional kinetics the meaning of each and every term. Now let's apply this here. Now we have, as we apply the acceleration, we have acceleration of P with respect to ground. Our P is our collar. So we'll write acceleration of collar with respect to ground, this is a vector equation, is equal to acceleration of P with respect to B. That is acceleration of collar with respect to rod. So we'll write acceleration of collar with respect to rod. Acceleration of collar with respect to rod plus acceleration of O dash with respect to J. Our J is ground. So O dash and ground are at same position. Okay. So their velocity, they are not moving with respect to each other. So they are at rest with respect to each other. So acceleration of O dash with respect to ground will be 0 because O dash is fixed in ground. So this term is over. So we have alpha, acceleration of beta, that is acceleration of rod with respect to ground, cross product with RO dash P, that is radius vector drawn from O dash to collar or O dash collar, bracket close, no, minus angular velocity of beta, that is angular velocity of rod with respect to ground square, and radius vector RO dash O dash to collar, plus twice angular velocity of beta with respect to ground, that is angular velocity of rod with respect to ground, vector cross product with, its cross product with RO dash P, that is radius vector drawn from O dash to collar. This is the expression for acceleration. Let's put the terms down. So we have acceleration of collar, acceleration of collar with respect to rod. Yes, there is a little correction here that we have to write here. The expression is twice omega beta with respect to ground cross product with velocity of P with respect to beta. This was the expression. Yes, I'm sorry for making this error here. So this will be, the correct term here will be velocity of, so we have velocity of P with respect to B, that is velocity of collar with respect to B, beta, and our beta is rod, that is velocity of collar with respect to rod. Okay, that's fine. So now put the expressions. Acceleration of collar with respect to rod. Do we know the acceleration of collar with respect to rod? Yes, that is 3 meter per second square, and its direction is along x-axis. So it is 3i cap. So this is done. Plus acceleration of rod with angular acceleration of rod with respect to ground. The angular acceleration of rod with respect to ground is given as 2 radian per second square, but it will be minus 2 k cap because it's along negative z direction with the by right hand square rule. Its cross product with RO dash C, the radius vector from O dash to C, that is 0.2 I cap. So this is 0.2 I cap. This is done. Minus omega of rod with respect to ground. Angular velocity of rod with respect to ground is 3, and it's only magnitude 3 square meters. So what we can write here is This is, and r o dash c, that's multiplied by o dash c, that is 0.2 I cap.
Okay.
Okay, so this is r o dash c. R o dash c is the radius vector drawn from o dash to c, and that's equal to 0.2 I cap. So it will be multiplied by 0.2 I cap plus twice angular velocity of beta, angular velocity of rod with respect to ground. That's equal to how much? The angular velocity of rod with respect to ground is equal to minus 3k cap. Cross product with, this is important, velocity of collar with respect to rod. The velocity of the collar with respect to rod is equal to how much? That's equal to 2 meter per second along x-axis. So it will be 2 I cap. Okay, so this will be 2 I cap, velocity of collar with respect to rod. Now let's solve it very quickly. So this will be 3I, that is k cross I. K cross I is j. So this is minus 0.4. K cross I is equal to j cap. So this is minus 1.8 I cap. So this is k cross j, k cross I. K cross I is equal to j. So this is 3 2s are 6, 6 and 2 are 12. So this is minus 12. And k cross I is equal to j cap. So this is minus j cap. So as we go ahead, that will be equal, it will be, that will be, this is 3I and minus 1.8I. 1.8I minus 3.3I, that's equal 1.2 I cap. Okay, then we have minus 12 minus 0.4, that is minus 12.4 j cap. And this is equal to what? This is equal acceleration of collar. This is equal to acceleration of collar with respect ground. Okay, this is equal to acceleration of collar with respect to ground, and this is what we had to calculate. And if you look at your answers, that's here. Acceleration of collar with respect to ground is 1.2 I minus 12.4 g cap meter per second square. This is, so this is the second portion. The third portion is we have to find the Coriolis acceleration. I told you yesterday, the expression for Coriolis acceleration is, this term is called Coriolis acceleration. This term is called Coriolis acceleration. That is twice angular velocity of rod with respect to ground, and its cross product with velocity of collar with respect to rod. Okay, that for us, we have done it here. That is 2 minus 3k cap cross product with 2I cap. That's equal to how much? 3 to 6 and 12, that is minus 12, and k cross I is j cap. Okay, so Coriolis acceleration is equal, we write this as far as the Coriolis acceleration is concerned, the Coriolis acceleration in this case is equal to minus 12 meter per second square. And this completes our question. Okay, so this is how we'll be, and this is here, the Coriolis acceleration term in this case is minus 12 meter per second square. Okay, so this is how we have to solve all these questions, first writing the frames of reference. In the same way, I request my students that they solve this question themselves. Students should be in a position to solve this question themselves. The students should be in a position to solve now rest of the questions, like the question of aircrafts themselves. And the students, okay, these two problems I'm leaving as an exercise to my students, and from tomorrow we'll be taking up unsolved problems from this section. This is all for today. Thank you very much.